Welcome back to the second kinematics in one dimension video. In this one, we're going to talk about scalars and vectors. Most importantly, we're going to talk about distance and displacement, and then we're going to figure out what the difference between a speed and a velocity are. So start off with, you've probably never heard of a scalar before. So what is it? What's a vector? Scalars are going to be quantities that have a size or a magnitude only, but they have no direction. So in other words, these are things that have a size. They're like absolute values, okay? They have no direction. And an example is volume. You could walk into a store and ask for 5 gallons of paint, but no one would walk into a store and say, can I have 5 gallons to the right? It doesn't make any sense. Now, contrast that, vectors are things that have both size or magnitude and direction. So these things have an orientation that makes sense. The direction, in a math class at least, or in physics class, can sometimes be denoted with a plus sign or a minus sign. An example is force. So I can push with 5 newtons of force or 5 pounds of force, right? And it makes sense for me to say, let me push with 5 newtons of force to the right, or 5 newtons of force to the left. Or to give you another example, if I told you that I was pushing with a negative 5 Newton force, that just tells you I'm pushing, say, that direction. But if I told you I went to the store and I bought negative 2 gallons of paint, you would hopefully think that was weird. Like, I don't know what negative 2 gallons of paint even means. Right? Because volume is a scalar. Direction has no meaning in those. So let's look at some examples. Scalars have size only. And some examples are like mass. So if you're asked to get 5 grams of something, you don't worry about, like, is that 5 grams to the north? Like, there's no direction involved. Volume, distance, speed, temperature. If somebody's worried about if you have COVID or not, they don't say, "Ooh, your temperature is 98.6 south." Like, nah. Your temperature might be rising or falling like it does during the day, but that's not really a direction. That's a trend. Again, we wouldn't talk about, oh, I'm 98.6 to the left. Like, that just doesn't make sense. So the thing that you can't see because it's blocked out behind my beautiful face here is time. And I put a question mark next to time because we do actually talk about moving forward and backward through time. So in some sense, time seems to have a direction, but I put it in the scalar list because at least in physics 1, time is always a scalar. So my example for that is, you might say like, oh, I'd really like to go back in time, like 50 years ago in time. That would be fun to visit. But no one would say like, oh, I think I'd like to go 50 years to the left in time. Like, that's meaningless. Vectors, on the other hand, all have a size and a direction. So things like force or weight. Your weight points in a direction. It points toward the center of the earth. Displacement and velocity, we're going to talk about today. Things like acceleration. Sometimes we talk about deceleration. So acceleration and deceleration imply directions. And then momentum is another thing we will study later in this year. You've probably heard of it. Also has a direction. So let's start with a vector and a scalar, or in this case, a scalar and a vector. Distance. Distance is the difference between two positions. It's a scalar quantity because if you ask for a distance, you just want a length. That's it. So if I tell you that my house is just 1 mile from you, did I tell you where I live? The answer is no. If I told you that I'm 1 mile from you, I told you that I am somewhere on a circle of radius 1 mile from your exact position. So I haven't told you where I am. I've given you a set of positions where I might be. Right? So in math class, if I told you that I am 5 from you, that my distance is an absolute value of 5 miles from you, do you know whether to go negative or positive? And the answer is no, because both -5 and +5 have the same absolute value. So like in a math class, when you take the absolute value of a quantity, you are destroying the direction. And when I'm talking about a scalar, I'm talking about a quantity where the direction has been scrubbed out. Displacement, on the other hand, is the difference between your ending position and your beginning position. And the order is very important. It is always end minus beginning. It's a vector. So if you ask for a displacement, you expect a length and a direction. Okay? So that if I want to tell you my displacement, I have to tell you that my house is due east of you 1 mile. So I've given you a displacement by telling you the distance and the direction to head. So is that it? No, of course not. This is physics. Scalars, when you add them together, they add exactly as you would expect. 1 plus 1 equals 2. It's very simple. For example, if I tell you that I walked 2 meters to the left, and then I turned around and walked 3 meters to the right, I have walked 5 meters. No problem. We're all good there. Look, the direction is not important. You simply keep track of each step in the process, and then you add all those things together. What about vectors? What's different when you add them? Vectors include direction, and so you have to be really careful about how you deal with it. One way is that you're going to establish a reference frame, right? And you're going to probably set up some coordinates so that you can help add. Your displacement is always found by, order is important, end minus beginning, or by assigning directions, positive or negative, to your movement before you add. So you're setting up a reference frame. You're going to say, when I go to the left, that's negative, and when I go to the right, that's positive. Okay? Now, do you have to follow my directions? No. It's your reference frame. You call it whatever you want. Left is positive, right's negative, but whatever you decide, you have to stick to it. So if I walk 2 meters to the left and turned around and walked 3 meters to the right, then I have a displacement of 1 meter to the right. And I have to give you both pieces. I have to give you the distance and the direction, 1 meter to the right. So here I am. I'm going to walk 2 meters to the left. And then I turn around, walk 3 meters to the right. So where am I now relative to where I started? Where is my end compared to my beginning? And the answer is I am 1 meter to the right of where I started. So if we did this using some math, and I said, look, I'm right-handed, I make things going to the left negative. So I'm going to move -2, and then I'm going to turn around and move +3. So -2 and +3 gives me a +1, which is 1 meter to the right. Now, since I said +1, I gave you a direction. I said positive, and that is a direction in this class. What if you're left-handed and you're sinister, you enjoy doing things the opposite way? You would say, oh, well, when I went left, I was going +2 meters, and then I turned around and went -3 meters to the right. So +2, -3 is -1. Wait a minute, shouldn't -1 be over? No, because you set up your reference frame backwards. So a negative number means to the right. So when you said that you moved -1 meters, you gave me a direction, and you had already established your reference frame, so everyone should be able to figure out what you're doing. Summary. Scalars add up exactly as you would expect. Direction doesn't matter. You simply keep track of all your individual motions and add them up. Vectors only depend on where you end and where you start. You really don't care what all the steps are in the in-between. You only need to know beginning and end, or end and beginning. Speed and velocity. We all pretty much know what a speed is. It's how fast you're going, right? So, but are speed and velocity the same thing? No. If they were, we wouldn't need two separate terms. Speed is going to be a scalar. So you could say, look, I'm moving at 60 miles an hour. That's your speed. right? There's no implied direction. I just told you I'm moving at 60 miles an hour. Velocity, on the other hand, is a vector. It needs a speed of 60 miles an hour, and it needs a direction. So let's say I put some trig in here, and I say I'm moving at 30 degrees north of east. Speed is just distance divided by time. When we say miles per hour, I'm saying my distance in miles and my time in hours. Velocity is displacement over time. So what's my change in position, end minus beginning, divided by my time? So let's do some math. Speed is equal to distance divided by time. Now, whenever you're trying to figure out what variable should I use, physics always picks the worst possible ones. So they picked v to be a speed variable. You probably would have picked s, but s is used other places, so v is your speed. And if it's a scalar, it will usually be normal font, no bold, no italicized, nothing. Okay, and we're just going to say speed is equal to distance divided by time. Velocity, on the other hand, is a vector. So different people use different notations for vectors. In this case, I italicized the v, and I put an arrow over top. Some people will also might boldface it, but they want to make it known that it's different, right? They want to bring your attention to say, hey, this is weird, so that you know this is a vector quantity. So College Board always makes them italicized, and most things they put an arrow over top also. They're not 100% constant with that, but if you see an arrow or an italic variable, it's probably a vector. So displacement is your change in your position. So I'm going to use a triangle or a delta. It's going to be delta x over delta t. And the x has an arrow over it because that is a displacement, which is also a vector. And time is a scalar, no arrow. So the real math is I'm going to take my end position minus my beginning position and my ending time minus my beginning time. So I chose to use subscripts of 2 and 1. Some books will use an F for final and an I for initial, or an F for final and a B for beginning, or a 1 for the final and a 0 for your beginning. So the subscripts change depending on what source you're using, but it's always a final minus an initial, okay? End minus beginning. So what's my speed? Earlier I said that I walked 2 meters to the left, turned around, moved 3 meters to the right. You have no idea what my speed is. So let's go further. What if I told you I did all that motion in 10 seconds because I was timing myself? So my speed is my distance divided by my time. And my distance was 2 meters to the left plus 3 meters to the right. That gives me 5 total meters of distance. I did it all in 10 seconds. That is 0.5 meters per second. Okay, so that's /m/s. It means per. I say it, but I don't like it. If we were in class together, I would actually force you to say meters in 1 second. Because until you get it in your brain, per doesn't always have a meaning. It's just something people say. So this is 0.5 meters in 1 second, right? It's a ratio. How far did you go in 1 second? But what was my velocity? So velocity involves direction. It's a displacement. So I'm going to stick with my original reference frame. I went negative 2 meters to the left, turned around and went 3 meters to the right, and I did that in 10 seconds. So my displacement was positive 1 meters in 10 seconds. So my velocity was 0.1 meters in 1 second to the right, or positive 0.1 meter in a second, right? Now, you can use either way. If you write a plus sign, you have implied a direction. If you say that it's to the right, you have stated a direction, you're okay either way. If you just left it as 0.1 meter per second, you're in dangerous territory because they asked for a vector, they asked for a velocity, and you didn't imply or state a direction. You just wrote a number, and that looks suspiciously like a scalar. So when you're asked for a vector, make sure that you're clear that it has a direction. Is it possible to have a speed and no velocity? So could I tell you, hey, you know what? I'm right now moving at 60 miles an hour. And you to say, well, hold on, your velocity is 0 right now, both at exactly the same time. That I'm moving at 60 miles an hour and I have no velocity. Sounds crazy, but yes. Here's how it's going to happen. If I'm moving at 60 miles an hour in my car in a perfect circle, I start, let's say, at the 12 o'clock position on this circle, and I move at 60 miles an hour constant. Like I put it on cruise control. This thing never leaves 60 miles an hour. When I arrive back at the 12 o'clock position, my displacement is now 0. I started at 12 o'clock position and I ended at 12 o'clock position. So my displacement is nothing. So even though I had this huge distance and I was moving really fast, my velocity is nothing at that instant. At all other points on that circle, I had a displacement. I was not at my beginning place. And so I had both a speed and a velocity. But in this one special case, I had a speed, no velocity. Can we turn it around? Is it possible for me to say that, hey, I have a velocity of 60 miles an hour to the left, and you say, no, your speed's nothing. And for both of those things to be true at the same time? Nope, can't happen. Here's why. A velocity is a speed and a direction. So if you have a velocity, you've got both, right? This is a square and a rhombus problem. All squares are rhombuses, but not all rhombuses are squares. So if you have a velocity, you definitely have a speed. But if you have a speed, there are some special cases where you do not have a velocity at the same time. Will two separate observers always agree on the speed of an object? So let's say I'm looking out my front door and there's a car going 25 miles an hour down the street with a dog sitting in the passenger seat. And I say, dog's moving 25 miles an hour. What's the passenger saying if the dog is sitting on the passenger's lap? The dog starts in the passenger's lap, and a couple seconds later, the dog is in the passenger's lap. So the passenger would say, this dog has no speed, right? It has not moved, has covered 0 distance, right? So it's possible for the passenger in the car to say that the dog is not moving, even though I say that it is. Or if you've ever been in an airplane, let's say they pour you a glass of water, stick it on your tray. That glass of water is just sitting there. It looks like it's standing still. But you know, if you want to be honest, that thing's actually moving at about 400 miles an hour. It's in an airplane at 30,000 feet, right? It's flying through space. But you could look at it and say, well, it's just sitting on my tray table doing nothing. So depending on what reference frame you pick, people can give different answers for the speed of an object and both be correct. Will they agree on the velocity of an object? Oh, definitely not. We can't even agree which way is right or which way is up. Like people in Australia are going to differ with the direction of up from people in the United States, right? If I told two people in one in America and one in Australia to point to up, and we took a picture from the moon, those two people are not pointing in the same direction. So if we can't agree on directions, usually, there's no way we're going to agree on a vector quantity. So two people can give two different answers for a vector and both be correct. Okay, so to summarize, if you're asked to find speed, that's just a velocity with the direction stripped out. Okay, or it could be the absolute value of your velocity. Basically, you're always looking for the difference between a vector and a scalar. And if you're asked to find a vector, be careful about the trick questions, okay? Because direction is really important, and it's always end minus beginning. Okay, bye-bye.